Hey guys, today we're going to look at 9.2 and 9.3, which is about graphing inverse variation. The essential question for today is how do we graph rational functions? First things first, let's look at some inverse variation translations. Every graph is going to start with y equals, and then if you're graphing inverse variation, the graph takes the form k over x minus b plus c. And it's a translation of the graph y equals k over x, which is of course inverse variation. And it's translating that graph by b units horizontally and c units vertically. And just like before, b is going to look like it's operating backwards because in our formula here there's a negative in front of the b. C, on the other hand, will look like it's doing what we think it would be doing because in the formula, C has a plus sign in front of it. The vertical asymptote is x equals b, so again, if it says x minus 7, the minus is part of the formula. The asymptote would be x equals positive 7. And the horizontal asymptote is y equals c. Here's a page from our book. For example, let's say that we want to graph y equals 1 over x minus 2 minus 3. Well, 2 is down here where the b is, and the minus is there. We know the minus is part of the formula, so we know the value of b is going to be 2. Minus 3, the 3 is over here where the c is, but there's a minus sign in front of it, so the value of c is going to be negative 3. Since b is going to be the vertical asymptote is x equals 2. C, the horizontal asymptote in this case, is y equals negative 3. So what do? We imagine graphing y equals 1 over x, which you can check with your calculator. And then we just move it over. In other words, drawing one of these graphs is as easy as sketching the asymptotes and plotting a couple of points. And all of them will take this shape where you kind of have the asymptotes crossing, and then you have one graph going close to each asymptote here, and another part of the graph getting close to each asymptote over here. So it looks like the graphs have two parts. Rational function graphs. Inverse variation graphs are examples of rational function graphs that take that funny shape. A rational function is all of this stuff here. But basically, in easy terms, a rational function is a ratio of functions, where you have a function on the top and a function on the bottom. And that's the definition that you need to know. A rational function has a function on the top and a function on the bottom. Rational function graphs have this idea of continuity. And graphs of rational functions can be continuous or discontinuous. If it's continuous, that means that you could draw the entire graph without lifting your pencil from the paper. So if we look at these three graphs here, go ahead and you try it. Which ones do you think are continuous and which ones do you think are discontinuous? I'll give you a couple of seconds and then reveal the answers. Hopefully these are the answers you got. You can tell the one on the left you could definitely draw in one motion. However, the one in the middle, you'd have to lift up your pencil to draw this side, this other side, and the side in the middle. So it's discontinuous. And on the right again, you'd have to lift up your pencil to draw the left-hand side versus the right-hand side, so it is also discontinuous. Now let's talk about points of discontinuity. What we need to do is we need to analyze the denominator of the rational function. And we want to look for values of x that would cause the function to be dividing by 0. So basically what would we do? We set the denominator equal to 0 and say, hey, what does x have to be to make this equation work? The values that we find for x are called the points of discontinuity. These will become either vertical asymptotes or holes in your graph, and we're going to figure out how to tell which is which. first let's practice finding them. For example, y equals 1 over x squared plus 2x plus 1. First things first, we take our denominator and we set it equal to 0. Now notice that this is a square right here. Leading term has a square on it. So we know that we could use the quadratic formula or factor or completing the square. Let's try factoring first. If we look at it, we see, oh hey, what multiplies to 1 and adds to 2? Well, 1 times 1. So this item right here can become x plus 1 times x plus 1. X plus 1 equals 0, or x plus 1 equals 0. So we have to solve one problem. So x plus 1 equals 0. So x is negative 1. So we would have a point of discontinuity, a vertical asymptote, or a hole where x was worth negative 1 on our graph. Here's a you try it. Again, I'll pause, give you a chance to try it on your own, and then you can come back and check your answer. Hopefully this is what you got. Hopefully you realized when you solved this problem you ended up getting x equals the square root of negative 1, hence our imaginary unicorn right here. Since the square root of negative 1 is not a real number, there is no point of discontinuity. In other words, any value that you put in here for x will never make the denominator 0. Try it. Pick any value you want. You're not going to get a 0 down there. And that means that the graph will not be discontinuous. It will go on forever. You could draw it without lifting your pencil from the paper. Okay, now let's decide how to tell if vertical asymptotes or holes will exist. First of all, vertical asymptotes occur at the zeros of the denominator. So back in that last slide when we had x equals negative 1, that would make the denominator 0. Holes happen if you take a vertical asymptote and that same value that makes a 0 in the denominator also makes a 0 in the numerator. Then it goes from being a vertical asymptote to being a hole. So if we look at this example right here, if we look at the bottom, you can tell that if x is 2 or if x is 1, it's going to cause the bottom to have a value of 0. Now up at the top, we see that this thing right here, if x is 2, it's also going to cause the top to have a value of 0. So since x equals 2 makes both the numerator and denominator 0, there's going to be a hole where the function crosses the line x equals 2, and there's the hole. On the other hand, if x is 1, it's only going to make the denominator equal to 0, and so when x equals 1, there's a vertical asymptote at that point on the graph instead of a hole. Now, vertical asymptotes are not the only ones that have rules. We also have horizontal asymptote properties. And here we compare the degrees of the numerator and the denominator. Numerator, denominator, numerator, denominator, denominator, numerator. If the numerator has more degrees than the denominator, there is no horizontal asymptote. If the numerator and the denominator have the same amount of degrees, there's an asymptote at y equals a over b, where a and b are the coefficients of the highest terms in the numerator and denominator. And if the denominator has more degrees than the numerator, there's an asymptote at y equals 0. No rational function has more than one horizontal asymptote, and it's because it's governed by these rules here. One of these three things is going to happen. Either the degrees in the numerator is greater, less than, or equal to the degrees in the denominator, so there's only one possible asymptote that can happen for any rational function. Sketching graphs, a couple of rules to keep in mind. First thing you want to do is place the horizontal asymptote. Second thing you want to do is place the vertical asymptote and or holes. Remember that these asymptotes you can sketch with a dashed line. The zeros of the numerator will be your x-intercepts, so they will intercept the x-axis. And then all you do to sketch the actual curves themselves, the blue things in the picture, just pick a few values of x near the asymptotes to test. Your goal is to plot as few points as necessary that will allow you to sketch the basic shape. And again, you could use your calculator's y equals button and then look at the graph menu to figure out the table. Last but not least, here are some U-triads. We want to know, is the value in column A less than, greater than, or equal to the value in column B? So I'm going to pause this, give you a chance to try them on your own, and we'll come back to the answers. Hopefully for this first one, this is what you found. If you set 3x plus 7 equal to 0 and solve for x, if you set 2x equal to 0 and solve for x, you will find that the value of x over here is less than the value of x over here. Since the denominator is where discontinuities come into play, all we care about is that part of the function. For this second one, hopefully you were able to look at the denominator again, x squared minus 1. You could use the difference of two squares to turn this denominator into x minus 1 times x plus 1. You find there were 2 points of discontinuity. Over here, maybe you remembered from our unicorn example that x squared plus 1 had 0 points of discontinuity. Therefore, 0, 2, 0 is less than 2. And for this last guy, hopefully again you look at the denominator. There's 2 points of discontinuity here. There's 2 points of discontinuity there. In neither case do the points of discontinuity, the zeros of the denominator, match the zeros of the numerator. So 2, 2, they're going to be equal.